Our final form of heat transfer is radiation. That is, energy transfer by electromagnetic waves. You've experienced this whenever you've sat in front of a fire or when you've laid out in the sun. And as you'll learn later in our electromagnetic waves unit, this radiation includes all kinds of electromagnetic radiation, not just the infrared radiation that you feel as heat, but also radio waves, microwaves, visible light, and more. And the interesting thing about radiation as a means of heat transfer is that unlike the other forms, it doesn't need matter. It can travel through a vacuum. Now, heat transfer by radiation also has a fairly simple equation that relates the heat transfer to the temperature. And this is the Stefan-Boltzmann equation. It says that the heat transfer delta Q over delta T is equal to the product of two constants, E and sigma, multiplied by the surface area of the object times the temperature of the object to the fourth power. Now, E is the emissivity. It's a number between 0 and 1 that increases with the darkness of the surface of the object. So, amazingly, when the object is completely black, we're going to have maximum heat transfer from radiation. The constant sigma is called the Stefan-Boltzmann constant, and here it's given by 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth. And of course, as we've already mentioned, the A is the surface area of the object. So the important thing to remember here is the rate at which an object radiates energy is proportional to the fourth power of the absolute temperature of the object.